Today, we are diving into the fascinating world of braking systems. Whether you are a car enthusiast or simply curious about how your vehicle stops, this video is for you. So let's get started. Modern cars have brakes on all four wheels, operated by a hydraulic system. The brakes may be disc type or drum type. The front brakes play a greater part in stopping the car than the rear ones, because braking draws the car's weight forward onto the front wheels. Many cars therefore have disc brakes, which are generally more efficient at the front and drum brakes at the rear. All disc braking systems are used on some expensive or high-performance cars, and all drum systems on some older or smaller cars. Let's move on to the hydraulic brakes. A hydraulic brake circuit has fluid-filled master and slave cylinders connected by pipes. When you push the brake pedal, it depresses a piston in the master cylinder, forcing fluid along the pipe. The fluid travels to slave cylinders at each wheel and fills them, forcing pistons out to apply the brakes. Fluid pressure distributes itself evenly around the system. The combined surface pushing area of all the slave pistons is much greater than that of the piston in the master cylinder. Consequently, the master piston has to travel several inches to move the slave pistons the fraction of an inch it takes to apply the brakes. This arrangement allows great force to be exerted by the brakes, in the same way that a long-handled lever can easily lift a heavy object a short distance. Most modern cars are fitted with the twin hydraulic circuits with the two master cylinders in tandem in case one should fail. Sometimes one circuit works the front brakes and one the rear brakes, or each circuit works both front brakes and one of the rear brakes, or one circuit works all four brakes and the other the front ones only. Under heavy braking, so much weight may come off the rear wheels that they lock, possibly causing a dangerous skid. For this reason, the rear brakes are deliberately made less powerful than the front. Most cars now also have a load-sensitive pressure limiting valve. It closes on heavy braking raises hydraulic pressure to a level that might cause the rear brakes to lock and prevents any further movement of fluid to them. In advanced cars, they may even have complex anti-lock systems that sense in various ways how the car is deaccelerating and whether any wheels are locking. Such systems apply and release the brakes in rapid succession to stop them locking. Let's move on to the power-assisted brakes. Many cars also have power assistance to reduce the effort needed to apply the brakes. Usually, the source of power is the pressure difference between the partial vacuum in the inlet manifold and the outside air. The servo unit that provides the assistance has a pipe connection to the inlet manifold. A direct acting servo is fitted between the brake pedal and the master cylinder. The brake pedal pushes a rod that in turn pushes the master cylinder piston. But keep in mind that the brake pedal also works on a set of air valves, and there's a large rubber diaphragm connected to the master cylinder piston. When the brakes are off, both sides of the diaphragm are exposed to the vacuum from the manifold. Pressing the brake pedal closes the valve linking the rear side of the diaphragm to the manifold and opens a valve that lets in air from outside. The higher pressure of the outside air forces the diaphragm forward to push on the master cylinder piston and thereby assists the braking effort. If the pedal is then held and pressed no further, the air valve admits no more air from outside, so the pressure on the brakes remains the same. When the pedal is released, the space behind the diaphragm is reopened to the manifold, so the pressure drops and the diaphragm falls back. If the vacuum fails, because the engine stops, for example, The brakes still work because there is a normal mechanical link between the pedal and the master cylinder, but much more force must be exerted on the brake pedal to apply them. Some cars have an indirect acting servo fitted in the hydraulic lines between the master cylinder and the brakes. Such a unit can be mounted anywhere in the engine compartment instead of having to be directly in front of the pedal. It, too, relies on manifold vacuum to provide the boost. Pressing the brake pedal causes hydraulic build up from the master cylinder. A valve opens and that triggers the vacuum servo. Let's move on to the disc brakes. A disc brake has a disc that turns with the wheel. The disc is straddled by a caliper, in which there are small hydraulic pistons worked by pressure from the master cylinder. The pistons press on friction pads that clamp against the disc from each side to slow or stop it. The pads are shaped to cover a broad sector of the disc. There may be more than a single pair of pistons, especially in dual circuit brakes. The pistons may move only a tiny distance to apply the brakes, and the pads barely clear the disc. When the brakes are released, they have no return springs. Rubber sealing rings round the pistons are designed to let the piston slip forward gradually as the pads wear down, so that the tiny gap remains constant and the brakes do not need adjustment. Many later cars have wear sensors, leads embedded in the pads. When the pads are nearly worn out, the leads are exposed and short-circuited by the metal disc, illuminating a warning light on the instrument panel. With regards to the drum brake, it has a hollow drum that turns with the wheel. Its open back is covered by a stationary backplate on which there are two curved shoes carrying friction linings. These shoes are forced outwards by hydraulic pressure moving pistons in the brake wheel cylinders, so pressing the linings against the inside of the drum to slow or stop it. Each brake shoe has a pivot at one end and a piston at the other. A leading shoe has the piston at the leading edge relative to the direction in which the drum turns. The rotation of the drum tends to pull the landing shoe firmly against it when it makes contact, improving the braking effect. Some drums have twin leading shoes, each with its own hydraulic cylinder. Others have one leading and one trailing shoe with a pivot at the front. This design allows the two shoes to be forced apart from each other by a single cylinder with a piston in each end. It is way simpler but less powerful than the two leading shoe system and is usually restricted to rear brakes. In either type, return springs pull the shoes back a short way when the brakes are released. Shoe travel is kept as short as possible by an adjuster. Older systems have manual adjusters that need to be turned from time to time as the friction linings wear. Later brakes have automatic adjustment by means of a ratchet. Drum brakes may fade if they are applied repeatedly within a short time. They hit and lose their efficiency until they cool down again. Discs, with their more open construction, are much less prone to fading. Let's move on to the handbrake. Apart from the hydraulic braking system, all cars have a mechanical handbrake acting on two wheels, usually the rear ones. The handbrake gives limited braking if the hydraulic system fails completely, but its main purpose is as a parking brake. The handbrake lever pulls a cable or a pair of cables linked to the brakes by a set of small levers, pulleys, and guides, whose details vary greatly from car to car. A ratchet on the handbrake lever keeps the brake on once it is applied. A push button disengages the ratchet and frees the lever. On drum brakes, the handbrake system presses the brake lining against the drums. Disc brakes sometimes have a comparable handbrake arrangement, but because it is difficult to place the linkage on a compact caliper, there may be a completely separate set of hand brake pads for each disc. Now let me give a detailed summary of the braking system. The braking system is a crucial component of any vehicle, responsible for reducing the speed or bringing it to a complete stop. It plays a vital role in ensuring the safety and control of the vehicle, as well as the passengers and other road users. The braking system works by converting the kinetic energy of the vehicle into heat energy through friction, thus slowing down or stopping the vehicle's motion. Now let's take a look at the components of the brake system. Let's dive deeper into the brake pedal, which is the first component. It is an essential input device that connects the driver to the braking system. When you press the brake pedal, you initiate a chain of events that ultimately lead to the vehicle's deceleration or stopping. The brake pedal is strategically positioned within the driver's reach, located on the floorboard in front of the driver's seat. It is designed to be easily accessible, allowing the driver to apply braking force quickly and effectively. The brake pedal serves as the command center for the braking system. When you press down on the pedal, you exert force that is transferred to the master cylinder, initiating the braking process. The amount of force applied to the pedal determines the intensity of braking force delivered to the wheels. In modern vehicles, the brake pedal is typically engineered to provide a progressive feel, meaning that as you apply more pressure, the braking force increases in a smooth and predictable manner. This design allows for precise control over the vehicle's deceleration and enhances overall driving experience. Furthermore, advancements in brake pedal technology have led to the incorporation of features such as pedal travel sensors. These sensors provide feedback to the vehicle's electronic control systems, allowing for more refined braking interventions, especially in systems like anti-lock braking (ABS) or electronic stability control. It is important to note that the brake pedal is directly connected to the brake booster, which assists in amplifying the force applied by the driver. The brake booster, usually located between the brake pedal and the master cylinder, utilizes a vacuum created by the engine or an electric motor to enhance braking performance. This makes it easier for the driver to apply the necessary force, particularly in situations requiring sudden or emergency braking. The second component is the brake booster. It is a vital component found in most modern vehicles that enhances the force applied by the driver on the brake pedal. The brake booster plays a crucial role in making braking easier and more efficient. The purpose of the brake booster is to amplify the force exerted by the driver on the brake pedal, allowing for effective braking with minimal effort. It achieves this by utilizing either vacuum pressure from the engine or an electric motor, depending on the vehicle's design. In most vehicles, the brake booster operates using vacuum pressure. It is connected to the intake manifold of the engine, which generates a vacuum during the combustion process. This vacuum is harnessed by the brake booster to create additional force for the braking system. When you press the brake pedal, the force is transmitted to the brake booster. The vacuum pressure assists in multiplying the force, resulting in a higher overall braking force being applied to the master cylinder. This amplification enables the driver to achieve effective braking without requiring excessive physical effort. In some modern vehicles, an electric brake booster is employed instead of a vacuum-based system. The electric brake booster utilizes an electric motor to generate the necessary force. It operates similarly to the vacuum brake booster, amplifying the input force from the brake pedal and transmitting it to the master cylinder. One advantage of an electric brake booster is that it can provide more precise control over the braking force. It allows for integration with electronic control systems, enabling advanced features such as brake-by-wire technology and regenerative braking in hybrid or electric vehicles. It is important to also note that the brake booster is designed to operate even if there is a loss of engine power or vacuum. In such situations, a reserve vacuum supply or an electric backup system ensures that braking assistance is still available to the driver. Now let's take a closer look at the master cylinder, which is also a critical hydraulic device that is connected to the brake pedal. The master cylinder plays a key role in converting the force applied by the driver into hydraulic pressure, which is then transmitted to the brakes. The master cylinder is typically located in the engine compartment, mounted on the firewall or bulkhead, close to the brake pedal. It is directly connected to the brake pedal via linkage or a push rod mechanism. When the driver applies pressure to the brake pedal, the force is transferred to the master cylinder. Inside the master cylinder, there is a piston or a set of pistons that move in response to the applied force. As the driver presses the brake pedal, the pistons in the master cylinder are pushed forward. This forward motion creates hydraulic pressure by compressing the brake fluid that resides in the master cylinder. The master cylinder is designed with two separate chambers, each connected to a different hydraulic circuit. In most vehicles, one chamber is responsible for the front brakes, while the other is connected to the rear brakes. This configuration provides a redundancy system, ensuring that at least some braking force is available if there is a failure in one of the circuits. The master cylinder is also equipped with valves, typically known as proportioning valves or pressure differential switches. These valves regulate the flow of brake fluid and help maintain balanced braking between the front and rear wheels. Once the brake fluid is pressurized in the master cylinder, it is ready to be distributed to the individual brakes. The pressurized brake fluid is transmitted through brake lines or hoses, ultimately reaching the brake calipers or wheel cylinders at each wheel. It is important to note that the master cylinder operates within a closed system, ensuring that the brake fluid remains sealed and free from contamination. Regular maintenance, such as checking the brake fluid level and replacing it when necessary, is crucial to maintain the system performance and reliability. Let's move on to brake lines, which is an essential component of the braking system that plays a vital role in transmitting pressurized brake fluid from the master cylinder to the individual brakes located at each wheel. Brake lines are a network of metal or flexible hoses that form a pathway for the brake fluid to flow. They are typically made of steel or other durable materials that can withstand high pressure and resist corrosion. In some cases, flexible hoses made of reinforced rubber or synthetic material are used to allow for suspension movement and accommodate wheel articulation. The brake lines connect the outlet of the master cylinder to the respective brake calipers or wheel cylinders at each vehicle. At each wheel, the brake fluid under pressure from the master cylinder flows through these lines to deliver braking force to the individual brakes. The brake lines are carefully routed throughout the vehicle to ensure efficient and reliable brake fluid transfer. They are strategically positioned away from moving parts, hot surfaces, and potential sources of damage to maintain the integrity. It is important to note that brake lines operate under high pressure, typically ranging from several hundred to several thousand pounds per square inch. As a result, they must be designed and manufactured to withstand these pressures to prevent leaks or bursts that could compromise braking performance. Over time, brake lines can be subject to wear, corrosion, or damage due to environmental factors, road debris, or accidents. Regular inspections and maintenance are crucial to ensure the brake lines are in good condition. Any signs of leak, cracks, or excessive wear should be addressed promptly by a qualified technician. In some vehicles, particularly those equipped with an anti-lock braking system, additional components may be present within the brake lines. These components, such as ABS sensors, solenoid valves, or modulators, are responsible for the precise control of brake pressure during ABS activation. Brake lines are the vital pathway that transport pressurized brake fluid from the master cylinder to the individual brakes. Their durability, proper routing, and maintenance are crucial to maintain the integrity of the braking system, ensuring reliable and responsive braking performance for safe driving. Now, let's delve into brake calipers, an essential component of disc brake systems. Brake calipers play a crucial role in the braking process by housing the braking pads and facilitating the conversion of hydraulic pressure into friction, ultimately slowing down or stopping the vehicle. In a disc brake system, each wheel is equipped with a brake caliper mounted over a rotating brake disc, also known as a rotor. The brake caliper straddles the brake disc and contains various components that work together to apply pressure on the disc. Inside the brake caliper, there are one or more pistons, typically made of metal or a combination of metal and rubber. These pistons are actuated by the hydraulic pressure generated by the master cylinder and brake fluid. When the driver places the brakes, the pressurized brake fluid is directed through the caliper, causing the pistons to move outward. As the pistons extend, they push the brake pads against the brake disc. The brake pads, typically made of friction material, are held in place by the caliper and positioned on either side of the disc. When the pad makes contact with the disc, friction is created, which generates a resisting force against the rotation of the wheel. This friction between the brake pads and the brake disc converts the kinetic energy of the rotating wheel into heat energy. The resulting heat is dissipated into the surrounding air, gradually slowing down the vehicle. It is worth mentioning that brake calipers are designed to apply pressure evenly on both sides of the brake disc to ensure consistent braking performance and prevent uneven wear. They incorporate mechanisms such as slide pins or guide bolts that allow the caliper to move slightly, accommodating for thermal expansion and ensuring proper alignment with the disc. Additionally, many modern brake calipers are equipped with features such as brake pad wear indicators or sensors. These indicators provide visual or electronic alerts to the driver when the brake pads require replacement, enhancing safety and preventing excessive wear on the disc. Brake calipers are crucial components in the disc brake system. Their design, materials, and proper functioning are essential for reliable and effective braking performance. We move on to brake discs, also known as rotors, which are crucial components of disc brake systems. Brake discs play a pivotal role in the braking process by providing a surface for the brake pad to clamp onto, generating friction and ultimately slowing down the vehicle. Brake discs are typically metal discs that are directly attached to the wheel hubs. They rotate with the wheel and provide a contact surface for the brake pads. When the driver places the brakes, the brake caliper squeezes the brake pads against the discs, creating friction. The friction between the brake pads and the brake discs converts the kinetic energy of the rotating wheel into heat energy. This heat energy is then dissipated into the surrounding air through brake discs. To enhance their performance and prevent brake fade, many brake discs are designed with ventilation. Ventilated brake discs have vents or fins located between the braking surfaces. These vents facilitate the flow of air around the discs, helping to dissipate heat more efficiently. The ventilation in brake discs help to mitigate the risk of brake fade. Brake fade occurs when the continuous application of brakes generates excessive heat, causing a decrease in braking performance. Ventilated brake discs allow for better heat dissipation, reducing the likelihood of brake fade and maintaining consistent Braking power. Brake discs come in various designs and materials such as cast iron, composite materials, or carbon ceramic composites. Cast iron is commonly used due to its excellent heat conductivity and durability. Composite materials and carbon ceramic composites are often employed in high-performance vehicles for their superior heat resistance and reduced weight. It's important to note that brake discs are subject to wear over time. Factors such as driving conditions, driving style, and the quality of brake pads can impact their lifespan. Regular inspection and maintenance, including checking the discs, thickness, and surface condition, are necessary to ensure safe and efficient braking performance. We move on to the anti-lock braking system, an important safety feature designed to prevent wheel lock-up during handbrake maneuvers. During handbrake maneuvers, ABS utilizes sensors, control modules, and a hydraulic system to help maintain control and steering ability, especially in emergency braking situations. When a driver applies the brakes forcefully, there is a risk that the wheels may lock up, causing a loss of traction and potentially leading to a skid. This can result in a loss of steering control and increased stopping distance, making it challenging to maneuver the vehicle safely. The ABS system continuously monitors the rotational speed of each wheel using wheel speed sensors. These sensors provide real-time feedback on the speed of each wheel to the ABS control module. During normal braking, all wheels rotate at similar speeds. However, if one or more wheels are on the verge of locking up, the ABS control module detects the significant speed differences and initiates the ABS intervention. When ABS intervention is activated, the control module modulates the hydraulic pressure to the individual brake calipers or wheel cylinders. This modulation is achieved through the use of solenoid valves that open and close rapidly, controlling the flow of brake fluid to each brake. By rapidly modulating the brake pressure, ABS allows the wheels to maintain rotational motion and prevents them from locking up. This enables the driver to maintain control and steer the vehicle, even under heavy braking. The ABS system operates on a cycle of sensing, modulating brake pressure, and resensing wheel speed. It continuously monitors and adjusts the brake pressure as needed until the vehicle comes to a stop or the driver releases the brake pedal. ABS is particularly effective in challenging road conditions such as wet, icy, or slippery surfaces. By preventing wheel lockup, ABS helps maximize the available traction between the tires and the road, enhancing overall braking performance and stability. It is important to note that ABS does not necessarily shorten the overall stopping distance. Instead, it helps the driver maintain control and steer the vehicle during emergency braking, potentially avoiding obstacles or collisions. ABS is now a standard feature in most modern vehicles, and it works in conjunction with other safe systems like electronic stability control and traction control system to provide enhanced safety and control. In conclusion, the ABS is a crucial safety feature that prevents wheel lockup during hard braking. By monitoring wheel speed and modulating brake pressure, ABS allows for controlled braking, maintaining steering ability and vehicle stability. ABS is designed to enhance safety and improve driver control, particularly in emergency braking situations or adverse road conditions. We move on to explore electronic brake force distribution, a technology that is integrated into many modern vehicles' braking system. EBD is designed to automatically adjust the distribution of braking force to each wheel, taking into account various factors to ensure optimal braking performance, stability, and control. When a driver applies the brakes, EBD works in conjunction with the anti-lock braking system to regulate the amount of braking force applied to each wheel. It takes into consideration factors such as vehicle load, weight distribution, road conditions, and braking system. The electronic brake force distribution system utilizes sensors, typically wheel speed sensors, and other sensors throughout the vehicle to continuously monitor various parameters. These sensors provide real-time data to the EBD control module, which analyzes the information and determines the appropriate distribution of braking force. Based on the data received, The EBD control module adjusts the brake pressure to each wheel independently. The adjustment is achieved by modulating the solenoid valves within the ABS hydraulic system, controlling the flow of brake fluid to each wheel. The primary goal of EBD is to optimize braking performance and stability. By distributing the braking force effectively, it helps ensures that each wheel contributes its maximum braking potential without compromising vehicle stability. For example, when braking during a turn, EBD can adjust the braking force to the outer wheels to compensate for weight transfer and maintain stability. Similarly, when braking on uneven road surfaces, EBD can allocate more braking force to wheels with better tractions, helping to prevent wheel lock or skidding. The electronic brake force distribution is particularly beneficial in emergency braking situations or when driving on slippery surfaces. By dynamically adjusting the brake force distribution, it maximizes the available traction and enhances the overall effectiveness of the braking system. It's worth noting that the EBD works seamlessly in the background without requiring any input or intervention from the driver. The system operates in conjunction with other braking technologies, such as ABS, to deliver a comprehensive and optimized braking experience. In summary, electronic brake force distribution is a technology integrated into modern braking systems. It automatically adjusts the distribution of braking force to each wheel based on various factors such as vehicle load, weight distribution, and road conditions. By optimizing brake force distributions, electronic brake force distribution ensures optimal braking performance, stability, and control, enhancing safety and overall braking effectiveness. Now let's discuss the parking brake, also referred to as the emergency brake, which is a mechanical brake system designed to provide an additional layer of security for parked vehicles and serves as an emergency backup in certain situations. The parking brake is separate from the primary braking system, which usually relies on hydraulic or electronic mechanisms, unlike the main brakes, which primarily operate on the wheels. The parking brake typically acts directly on the vehicle's drivetrain or wheels, depending on the design. The primary function of the parking brake is to prevent the vehicle from moving when it is parked or to provide emergency braking in situations where the main braking system fails or malfunctions. It is an important safety feature that adds an extra level of security and control. In most modern vehicles, the parking brake is engaged by either pulling a lever or pushing a button. The lever or button is typically located in the center console area between the front seats, although the precise location can vary depending on the vehicle's design. While the parking brake is engaged, it applies mechanical force to specific components of the drivetrain or wheels, effectively holding the vehicle in place. This prevents the wheel from turning freely and helps to prevent unintended rolling or movement, especially on inclined surfaces. The parking brake is particularly useful when parking on hills or slopes. By engaging the parking brakes, the vehicle's weight is distributed evenly across the braking system, reducing the strain on the transmission's parking pole or other locking mechanisms. In emergency situations, such as failure of the main braking system, the parking brake can serve as an alternative means of stopping the vehicle. Engaging the parking brake can help slow down the vehicle and bring it to a controlled stop, allowing the driver to regain control and potentially avoid a collision. It is important to note that the parking brake should not be used as a substitute for regular maintenance or repair of the main braking system. If the main brakes require attention, they should be serviced by a qualified technician to ensure proper functionality and safety. In conclusion, the parking brake, also known as the emergency brake, is a mechanical brake system independent of the main braking system. It is primarily used to secure the vehicle when parked and serves as an emergency backup in situations where the main braking system fails. Engaging the parking brake provides an additional layer of security and control, preventing unintended rolling or movement of the vehicle. The brake fluid, which is a specialized type of hydraulic fluid, plays a critical role in the operation of the hydraulic braking system. It serves as a medium for transmitting the force from the brake pedal and master cylinder to the brake calipers or wheel cylinders, enabling effective braking. Brake fluid is specifically formulated to meet the demanding requirements of the braking system. It possesses characteristics that make it highly resistant to heat, moisture, and compressibility, ensuring consistent and reliable performance under varying conditions. When the driver applies pressure to the brake pedal, it activates the master cylinder, which in turn pressurizes the brake fluid. This pressurized brake fluid is then distributed through the brake lines to the brake calipers or wheel cylinders at each wheel. The hydraulic force exerted by the brake fluid causes the piston in the calipers or wheel cylinders to move, applying pressure to the brake pads or shoes. This pressure is then transferred to the brake discs or drums, creating friction and ultimately slowing down or stopping the vehicle. Brake fluid operates in a closed system, meaning it circulates between the master cylinder and the brake components without being consumed. However, over time, brake fluid can become contaminated with moisture, dirt, or air, which can degrade its performance. Moisture is a common contaminant that can enter the brake system through microscopic pores in rubber hoses and seals, or during routine maintenance when the system is exposed to the atmosphere. Moisture in the brake fluid can lower its boiling point, potentially leading to the formation of vapor bubbles when the brakes are applied vigorously. This can result in a loss of braking efficiency or even brake fade. Regular maintenance and inspection of the brake fluid are crucial to ensure optimal braking performance and safety. It is generally recommended to have the brake fluid flushed and replaced according to the manufacturer's specification, typically every 1 to 2 years as indicated in the vehicle's maintenance schedule. During a brake fluid flush, the old fluid is completely removed and fresh brake fluid is introduced into the system. This process helps remove contaminants and ensures that the brake fluid maintains its desired properties. It is also important to note that the type of brake fluid used should comply with the vehicle's manufacturer's specification. Different types of brake fluid have specific characteristics and boiling points, and they are not interchangeable. Using the wrong type of brake fluid can adversely affect braking performance and may damage the braking system. In summary, brake fluid is a specialized hydraulic fluid that transfers the force from the master cylinder to the brake calipers or wheel cylinders, enabling effective braking. Regular maintenance, including brake fluid flushes and replacement, is essential to ensure the performance and longevity of the braking system. Monitoring the fluid's condition and adhering to the manufacturer recommendations helps maintain optimal braking performance and safety on the road. The last component is the drum brakes. Although drum brakes are less prevalent in modern vehicles, they are still used in certain applications, particularly for rear-wheel braking systems. Drum brakes function by utilizing brake shoes that press against the inside of a drum to slow down or stop the vehicle. The primary components of a drum brake system include the brake drum, brake shoes, wheel cylinder, return springs, and an adjuster mechanism. The brake drum is a cylindrical housing that is mounted to the wheel hub, and the brake shoes are positioned inside the drum. When the driver applies the brakes, Hydraulic pressure from the master cylinder is used to activate the wheel cylinder. The wheel cylinder expands, pushing the brake shoes outward against the inside surface of the brake drum. The brake shoes are curved metal plates that are lined with a friction material, typically made of heat-resistant materials such as asbestos, free organic compound, semi-metallic or ceramic materials. As the brake shoes make contact with the drum, the friction between the shoe lining and the drum generates resistance, which slows down the rotation of the wheel. To facilitate the release of the brake shoes from the drum when the brakes are not applied, return springs are used. These springs retract the brake shoes, allowing the wheels to rotate freely without any contact between the shoes and the drum. Additionally, drum brakes often incorporate an adjuster mechanism to compensate for wear over time. As the brake linings gradually wears down, the adjuster mechanism automatically adjusts the position of the brake shoes, ensuring consistent and optimal brake performance. While drum brakes have some advantages, such as simplicity and lower cost, they also have certain limitations. Drum brakes are generally less efficient at dissipating heat compared to disc brakes, which can result in reduced braking performance during prolonged or heavy braking. Furthermore, drum brakes are more prone to brake fade, a phenomenon that occurs when the continuous application of brakes generates excessive heat, leading to diminished braking effectiveness. This is particularly relevant in situations where repeated or sustained braking is required, such as when driving downhill for an extended period. In modern vehicles, drum brakes are more commonly found in the rear wheels, while the front wheels are typically equipped with more efficient disc brakes. This configuration optimizes braking performance and allows for better heat dissipation in the front, where the majority of the braking force is applied. Which, in summary, drum brakes are a type of braking system where brake shoes press against the inside of a drum to slow down or stop the vehicle. While less prevalent in modern vehicles, they are still used in some rear wheel applications. Drum brakes have their advantages and limitations, and they typically incorporate components such as brake shoes, a brake drum, wheel cylinder, return springs, and an adjuster mechanism. Understanding the characteristics and operations of drum brakes contributes to overall knowledge of different braking systems. That's all for today. We hope you enjoyed the video. Please hit the subscribe button for more videos like this.